Hi everyone, I'm Yaorong. Today I will talk about this paper rethinking the usage of normalization and dropout in the training of deep neural network. They can make novel method. Probably is not novel. This paper is published with a combination of the rational and dropout. They can prove it in a trick way to show that it can, to some extent, reduce neural information between the neurons, which is mostly the networks prefer. I will start with the motivation. How the idea came out from the author. As we know that deep neural networks is become larger for recent years because we want the models to have a stronger or better representation of the data features. So we try to make it deeper or wider. The problem is when you get more parameter into the model, you need more computation of it. So people were thinking of how to make the training process more efficient. This is a big area of doing this research. 5 to 30 years ago, LeQuinn has mentioned that by making the input neurons or the input data uncorrelated, more specifically whitening them, that helps improve the convergence of training on the network. The problem is, if you want to whiten this input, basically, generally we have a lot of neurons like 100,000 or even higher. When the dimensions increase at that level, then the whitening process becomes very computation expensive. As people working in training know that the group PCA is already take hours to reduce the dimension from tens of thousands to like 100 dimensions. So when training such big models, your whitening at each layer is almost impossible. Or more advanced, people thinking not only whitening, if we can make the inputs not only uncorrelated, but more specifically, it can be independent of each other. And this will significantly improve the representation in another level. Still, it's very computation expensive. Like we know informatics is based on objective of entropy or fast assay of the net entropy or non-Gaussian analysis. When you try to optimize or training based on this objective is really slow. So people if it's not using these techniques, you're trying to slow down by using a benchmark, which has demonstrated is very efficient on most of the networks. Based on this knowledge and others, these authors from this paper thinking that if we can make technique or more specifically some layers that can to some extent increase the independence between neurons, maybe not make them fully independent, but increase their dependencies. Will that improve the performance of the model? And at the end of this paper, we're also talking about something about benchmark, which is the location of where you put the benchmark in the networks is also will affect the convergence. Oh, before going to their models, I will mention again why this uncorrelated inputs matters. Let's consider the most basic model. It's just a linear regression model with EX, Y equals to AX, and probably have some noise. So by computing the gradient of by optimizing this problem, we can use just least square to computing least square to optimize this model and sound this transformation. And by computing the gradient descent gradient of this, we can from that, I will not go through how the grid is computed. This just the basic part. And the optimal solution of the transformation will finally located in this direction, the function two. So we can see that from the left-hand side is equal. The whole formula can be set as a times the covariance of x, which is the input neural, equals to the covariance between x and y. So this leads to a problem. If
what question? Remind me, what is y again?
Oh, y is just output. Y equals x, just a regression result.
So it's given, it's known.
Yes, it's given. It's just considered like a perception here. So not in a big model, big network. Linear transformation. Yeah.
Okay.
So, so in this condition, when a times the covariance of x, the problem is if the covariance matrix of the input is like for some neurons they are not independent, they are correlated. The covariance matrix of that will be not full rank, with is a rank deficient matrix. In this condition, the solution of A will not be unique. So when you put it into a very big network, like hundreds of layers, all of them there are a lot of this kind of layer exist. The optimization precise of A will be very unstable, and so the solution will be not unique, and the optimization precise will keep fluctuating. So this is why people prefer for uncorrelated inputs. And you can see that maybe when the covariance is just a full rank as works, for if you can make the input as uncorrelated as possible, just like when you consider informatics, we apply PC. So PC is not required for the IC process, but the PC will significantly improve the optimization process. This is why you try to make it full rank, and if you can make it all uncorrelated, that would be more preferred.
Can I just clarify one thing? What you're describing is not, it's not like they're doing regression on the different layers. It's just PCA on between layers. What this, the idea here is PCA between layers, not regression, because we don't know the output. We don't know why when we're training.
Was this precisely trying to say if the input is correlated?
Sorry, I couldn't understand.
It would be percent again, actually. Because here, the correlation of the input, if it's rank deficient, like low rank covariance matrix, so the solution of A will not be unique, because what this part is trying to say. So, and
sure, that is an issue, but I was referring to why. That why is the result we want, uncorrelated, but it's not given.
No, it's not. It's not an unsupervised learning. So it's just like perceptual. It's a linear regression. When we have the input, I was saying that when we have input, we have output, and we want to find the transformation that doing this regression. And if the input is uncorrelated, so the transformation solution can be unique, and it is not. The solution will not be unique.
Okay, so but what you're describing is not then something that's used during training between layers, or this is not patch norm yet. This is just background.
I think, Curtis, I think Yaorong is like, this doesn't relate to neural networks at all. He just wants to show us this inequality, covariance, input covariance transformed through the matrix linear transformation should be equal to the cross covariance of input and output.
Yeah.
I think that's kind of like, yeah, up in the air statement. It's not attached to anything yet. It's just an introduction. Right? Yeah, this is just like you're saying this holds, so this must hold on the ground truth for linear regression.
Yeah. Yeah, that's going to. So based on this, the author is thinking that they can create a layer that can encourage the independent between neurons. So what they do, they propose the IC layer is combined by a gas norm and dropout layer. So actually, they do not do any modification of these two techniques. They just keep it as what it is. Is the tricks in their methods is where you put it. So I will show this precise in their experiment how this will affect their results and why. And also, firstly, I will go through proof why this precise, why like that. It's mainly related. The theoretical proof part is related to the dropout layer. Why it can reduce neutral information when you set it there. And next, we will show some of the empirical result on the most popular data. So how the IC layer design? So as I mentioned before, the IC precise is combined with PSA with some rotation optimization. So they consider the combined batch normalization and the dropout will do kind of trying to get in close to this precise. This is how they describe in the paper, but I'm not very followed with the batch norm part because the batch norm part is necessary because you can get like the zero this for the inputs. And then they consider the dropout part will reduce the mutual information, which they mean that it can be, to some instance, I should add it here, replace the rotation part, which is from the IC optimization part. So I will explain why the dropout layer can do such kind of thing.
But isn't this what is already done by default? When people use batch norm and dropout, this happens anyways, right?
But so it depends on where you put it.
So this one puts the batch norm after activation function of the previous layer, right?
Mm-hmm. And so it should be. Generally, this one will put after the activation function. Well, for this paper,
yeah, this
basically called relevant.
Yeah, but it's after activation function here because the way they call it inputs, that means it has been already processed. But the order of dropout and batch norm, okay, it matters because you use everything in the normalization.
So this the theory part of we're trying to do. For mutual information definition here, I just attach the functions here. And for their theory is trying to say that because the dropout part is like for the neurons times with the Bernoulli distribution. So because for some ritual that neuron get activated or not. So they're trying to explain if the so xi hat represent the neurons after the dropout layer. So they're trying to say that to prove that mutual information after dropout will reduce information between neurons. And also, they mentioned about the entropy. The entropy I typed here, but I'm not quite sure why this single entropy of one neuron matters. Because generally, when we try and optimize assay algorithm, we prefer joint entropy of them. So, but I will still prove of that because I think it's showing that the entropy of the neurons are still fitting into in a high distance. And now, first I will go through the first of the mutual information part. So they try to divide mutual information after the dropout layer. and separate into three parts. So the first part of the summation of A1, which consider as the mutual information between when one neuron activated and another neuron is deactivated. So this mutual information of this part will be written as rhythm. So which means xi is activated as 1 and xj is deactivated with after dropout layer to be 0. Because it's based on Bernoulli distribution. So the probability of the pxj equals to 0 is a Bernoulli distribution which is purely depends on Bernoulli distribution, which is independent to when it's activated. So the top of the part can be represented as the independence of px activated times the pxj deactivated. So basically, when the top and the bottom of the log part will be the same, so it will be log 1. So the summation of the first part will be 0. Is that clear? Okay, so similar to the second part. So basically,
can you? I blinked. That's something else. What is sigma A1, sigma A2 again? Can you? Sorry. On the top equations, you have three components.
The sigma A1 is symmetric. It's kind of part of the equation. So when the one neuron, because after dropout,
you split the integral into you integrate one, and okay, A1 is just one of the
activated, and another A2 xi is activated. It's some parameters. I don't know. It's just in the network it's activated after dropout, and the xj is 0, which means drop out. So the mutual information between these two neurons, one is still kick, another one is drop out.
Yeah, what is A1? Can you some specific value or
A1 is just the neuron itself. We get some activation or layer there. We get a neural activate number instead.
all of those numbers?
Yeah, activate. There is a dropout layer there. All of the input, and there's a dropout.
Yeah, what you're summing over all possible values for that neuron in the batch, or
so the mutual information is between any two neurons, and for the sigma A1 part is consider the neurons that one is activated. The first one is activated, but the second one is not activated.
Yeah, you're but what is the sum over all of the values in the batch?
Yes. It's
in case A2, it's the reverse also.
Yeah.
True.
Yeah.
So they both have to be activated.
So you mean that after dropout, some nodes are getting activated and some are getting.
Yes.
Then you're trying to find the possibility of how many nodes are in this, how many true nodes or paired nodes, paired nodes have all this situation.
I'm not trying to count this number. I'm just
Because I mean the probability.
Yeah, no, she's not. He's trying to see how they affect mutual information. So those who are not in the pair, if one of them is not activated, they don't affect mutual information at all because it's 0.
Yeah.
Because they're independent already. But when they both on, then they
yeah. This is just a
so sigma A2 is the same.
Same.
It's just activation of the second. Like that.
well, for them the first two part will have 0 weight to the mutual information, and then comes to the third. So in this condition, both neurons are activated. So because we have this mutual information is computed after the dropout layer. So we consider a dropout layer, we represent it by using a Bernoulli distribution. So in this condition, the probability, the joint probability of these two neurons equals to the joint probability of these two neurons plus when the Bernoulli assign 1 to the two neurons. So basically, the probability will equals to p squared. P is a mean of the Bernoulli distribution. P squared times the joint probability of the two activating nodes. So by putting back to the mutual information definition, we can see that after the drop off, the mutual information between neurons are dropped to the p squared of this.
So I think it is my opinion. Like you how do you define A2? Since you're trying to say sometimes that
Well,
or sometimes
No. This is wrong notation, confusing notation. I agree with you. What I mean
the
is,
A1 doesn't matter. You can say if it's not 0, it's activated.
no, they're saying there are two neurons, 1 and 2. Integrate over all of their possible values. It's not that equals to A1. All of the possible values. It's a variable. It's not a constant.
so there might be more than 3 equal summation, right?
No, well, for two neurons, there are only 3 summations.
Oh, for 2 neurons.
For two neurons. It's looking only at 2 at a time.
And if you're looking pair by pair.
Pairwise initial information. Yes, exactly. It's not the general model.
So
Yeah, notation is heavy. I was also confused because when you write this, this is like, oh, this is the constant. But this is not a constant here. It's any possible value.
yeah. So Bernoulli distribution. So
No, you said the mean of the lambda, right?
yeah.
I think it's usually lambda. If you look at the no, that's Bernoulli.
Bernoulli distribution is the probability like with the probability of one small p here to the sign 1 and 1.
It's probability of effects.
Yeah, so for all this part, they are trying to show that the dropout layer will reduce the mutual information between the neurons. And then they're trying to show about entropy of the neuron. Actually, I don't know why they show this here because it's not much related to what they are used for, but I was still putting here. It's more like a what is exact but I will just go through it. For after the dropout layer, how the entropy will be affected. So entropy is defined as the summation of p times log p. So still we will consider two conditions of by computing the entropy, which is still the confused notation when a equals to 0, which means it's activated. When it's not, it's when 0 is deactivated. When it's the non-zero, it's activated. So they consider two parts of them. The first, I think if there's a title here, it should be summation of a equals 0. if A equals to 0, which the neuron is deactivated. So in this condition, this part will equal, because the 0 is signed by based on the gain generated by the Bernoulli distribution. It's like a dropout rate. So the P, the probability of xi equals 0 equals to 1 minus D. And by putting back into the entropy function, so the first part will be replaced by this one, because it's equal to the 1 minus D. These are okay, then for the next part is consider when A is not equal to 0. For the second part, it's just xi equals to A sum number computing. So this part, because we have shown that the P, when the neuron is activated, the probability of it is based on P is equal to P times the probability of the neuron before dropout layer. So it's written as this. So the whole part of this part can be written as this. And for the lower part, we'll separate it out and finally can get this one. So for the right hand side part, P times sigma of this part is just the entropy of the neuron before dropout. So it can be represented as this. And for this part, compared with the front, when this neuron deactivated, it's just the neuron of when like you have the summation of the neuron is represent the entropy of the Bernoulli distribution. So the entropy of the neuron after dropout will be equal to this. I know it's kind of impressive. Okay.
And that's so
is this growing or shrinking with P?
Yes, I also have this question. This paper do not have an explanation, but I think probably it should be going up because as they describe the mutual information is going down, but their entropy is based on finger neurons, not neurons. Quite sure it's going down. And they also talking about how this dropout precise will reduce the correlation between neurons. Do the same explanation precise. The correlation coefficient is defined as this for the one of the layers. Expectation of, because we include the dropout layer there. So after that, everything when the location we have is after. So the correlation of them represented this. Well, because we have the dropout rate, which is the thing. So the virus. Well, remember we mentioned that the IC layer is combined by a batch norm and the dropout. So before throwing to the dropout layer, the all the xi's are being normalized, so they have virus form. So after the dropout, the virus become P. So which means the expectation of the after the dropout layer, the expectation will become P squared times the of the expected before the dropout layer. So based on that part, the correlation coefficient between neurons after the dropout will also decrease. So this is what they're trying to show. This is all of their proof part. I think if you have any question, because other notations can. Not fully independent, they will try and make the reduce independence. Yes, good, because it's proof that the critical company or independent. And then the structure will work the experiment. So they applied the experiments on three benchmark data set, 710, 100, also the image. So architecture is based on the risk. There's the paper is 2019. So that and they're not trying to achieve like state of art performance of their adding the IC layer. They're trying to show that this IC layer can improve converge or the accuracy. So they will combine with the ResNet, the vanilla version of the ResNet from these two papers. It's just a ResNet version of more deeper ResNet architecture. And for the parameters in the IC layer, for all models, it will take the batch model have a relative parameter for training. And it's better for error conversion between them. And the total number of random kind of parameters in all of the models are the same. And for their applications, they kind of apply them to a different way. For the main, but it's not much different to the vanilla version of the ResNet, as we see that there's kind of the vanilla version of the ResNet. They were trying to have some input to the mapping connection to escape couple steps there. And from this paper, they're trying to say that this connection, when putting to different places, will affect how this converge and accuracy of the model. So all the parameters are the same using same optimization as Atom for the several data. But use the SGD for the image, and I will talk about it. And first, I will show the results. Anyone has questions?
I have a question on the significance of fractional. The proofs don't need by fractional. They only need dropout.
I realized that this morning.
Yeah.
I was thinking,
They always prove fractional does not.
But the fractional part is trying to like really showing the correlation part. It's not. But for the mutual information part, same stuff. But I think that was because it already considered them already normalized.
And do they have to be for proofs? They don't have to. Proofs will still be. Fractional is kind of random to what.
Well, for the fractional part, this they will mainly mention it in their discussion, like apply it before or after the division.
That sigma is bounded. Maybe maybe just for that. Okay.
So the correlation part was showing the distortion. Yes. There a conclusion that
So what I'm thinking is part of the transformation going down is from correlations. And therefore, not actually think like simple example, if you have compared to like that is correlated and becomes uncorrelated, there is a one-to-one match with the mutual information of those two variables. And as the correlation goes down, there is a predictable that amount that goes down. And they're one-to-one. There's no extra information. All the information is correlation. But there's that there's more information that is being used. It's all of that information.
No, I think their thing is not trying to compete with IC. More part is like what at the beginning mentioned for neural networks, they prefer uncorrelated performance. If they're independent, that is more better, but that will be more difficult. So I think from their conditions, it's just consider of the whitening process. It's not whitening, it's trying to decorrelate, but not specifically decorrelate. Because the dropout is very simple, it's just the deactivate neurons to zero. And they're trying to show that when some part deactivate, this condition of mutual information.
That's my point. If it's just decorrelating, whenever you decorrelate the variation of it, definitely itself. So is there more to it than just decorrelation? Because then you can call it IC.
Well, I don't think so.
But if there's like different kind of dependence between nodes and units, once the right storage it's fine. It's not necessarily spatial information the same examples, right? If like there's some information like the
Sure, right. It's not about how much.
it's about
Is it what is the driving force?
right
Is it lower correlation?
or the
Lower
right
information.
that in correlation
Well, kind of the other way around.
not like linear.
Here.
Probably wrong. I think. So I'm not sure because there's no rotation. Just like how the dropout.
I think it's also specific to one that
No,
for the results average over multiple batches.
I think it's in just one machine.
The proof of the one that
Yeah.
Well, because over multiple batches, the matrix A changes or transformation changes, right? It's a approximation. The batches are not in there.
but the batch is not the way the batch goes. It's not that it's some numbers that they don't know. There's some distribution.
No, those are values. That we marginalize. So the same neuron has multiple values. The multiple is the
They don't batch.
Yes, it will. It will change.
when you
Like we don't know the actual value to figure that.
until you push the batch through the
No, I don't know. There is a distribution for those things.
Yes.
What is the
Yes, this is based on the one layer in Vega. So reverse input is based on all before left. So the distribution is not fixed.
I think my point is those expectations over A. Are those days on one batch? Is there another over the batch?
Just the format.
I think it's a bit. It does not work. Everything.
So, and so for the first experiment is based on the pretend 100 data set. We can see that by stably change the layer within the we call IC layer there will improve the performance. There's no parameter change, everything doesn't change, just IC layer. So how we do that is like traditionally for the resonance, the connection is between here, but three different models. And it can be from before relevant, after relevant, or after the IC. And all of this three will have different effects, but it's better than this one. So there is vanilla version of resonance. And they're trying to test on two different resonances, different tips. And all of them are the baseline on the classification accuracy. And here is benchmark is not correlated. It's just kind of just yeah.
Yeah, it's a score.
Yeah, it's
So they're effectively adding a layer.
Actually,
No, they're not adding anything. They're just proving that if we are gonna already use layers in this order, we'll get where we'll get this.
yeah, we'll change the order of the let's do there. All the both of the resonant are there adding IC, what they call IC layers there. The resonance do have to drop all the rational.
Oh, Vaishnav is even worse.
Right. That A matrix we talked about the transformation. Where is that?
What? Which one? Which one?
Yeah. Think of linear regression or perceptron. That is transformation.
Where is that?
Yeah, the weights. But this is the CNN. This is the transformation. The pink ones are the peach height. And it's linear. CNN. No. There is nothing really proposed. There are only proofs. So the batch norm is tricky. It's a cheat, right? And I never thought about it until I looked at when they introduced this hyperbolic tangent norm, blah blah blah. But batch norm is Z score. The score, the input, whatever the input is, let's call it X. But then for each input, you have a parameter matrix. They call it gamma, but let's call it B. Oh no, let's call it A. And a biased matrix, exactly of the same size. So batch norm does this. It's scaling. First you use score, but then there is learnable scaling and learnable bias. So I don't know.
Yeah,
and they prove they use it.
yeah.
Yeah. So you're setting it to one, but then you're shifting it around the way you want and scaling it the way you want again. Those are learnable parameters per input, per neural base.
Well, I don't know because there is different correlation.
There is not, I mean, this is not the correlation part because A is not a linear transformation. It's an element-wise scaling.
Right. That's traditional, but the thing they're talking about here.
No. They say it doesn't analyze. if you do, they say, what I heard at least, they say this IC is batch norm dropout. So they do exactly the same, but they add dropout after batch norm. So IC is batch norm and dropout. Dropout doesn't do any transformation, doesn't do anything. It's just complete turning on and off the variables with some properties into zero. But then this extra skip connections make me, I don't know. It's, what's their explanation why they need all of those skip connections?
They're trying to put this thing in the discussion part, talk about the batch norm before. Because the rel here is matters. The batch norm before and after rel are different. Yeah, for sure.
Yeah, but we knew that before this paper changing.
Yeah.
But that makes I think that linear regression is
Oh, it's some transformation, that's what they're saying.
that the matrix is batch norm that it's not really
No, it's not a, it's just it's a scaling function per parameter.
so all of that stuff about linear regression.
No, linear regression is the pink peach color block. Wait. Or before. No, it's before. It's the input. They call input.
But not the second one.
Well, they assume that some input came from the left, right? Yeah, why did they order it like that? Okay, I see what's confusing. Why did they do this transformation before they gave it to linear transformation? Does it matter? Do they apply ReLU to the input data? And then do get IC, well, batch norm, bullet with dropout, and then linear transformation. It feels to me that it's insignificant. The only thing that's significant is the order of batch norm and dropout. Then, because you cannot do dropout before batch norm, you get Z-score.
This is converted Z result based on this based on the sample experiments. So it's information about this baseline of this of the relative IC and conductivity is the weight. It's a purple one. Generally will have a more stable train and can faster converge, especially at the beginning capital from epochs. And can reach that converging limit. Or units of yeah, it is true when I read it, I feel like it's some of your company already mentioned before that. But it's the this result. And for another experiment on internet data, we have some classes that are done training images. And on the 50,000 validation images, they're trying to show that top 5 of their model with IC. These IC layers can convert faster, especially at the first 30 epochs for both of this was top one, top one. I didn't prepare much for these two classes, just show them model there. I see and have a better performance and stuff. Yeah, so. The baseline models. Yeah, the architecture. Yeah, I checked in the paper because this one also makes me some use. Make sure that they use the exactly same architectures with the original version, but they change the IC layers with things of the professional method or dropout orders.
Yeah, but people had this argument of where to apply dropout and professional from the beginning. So people have tried all of the combinations without thinking about independence or uncorrelatedness. But in 2017, when we were smashing that paper, it was already, and I remember Dropout just came out a year ago. So people were, some people were applying after activation function, before activation function. This is exactly. Yeah. They're saying, okay, we're applying the after activation function, we're in this count, and then we're applying dropout after everything. That's all they're saying, but that's not the significance here. They didn't discover a new way. They just demonstrated, they just demonstrated that just generalization distance connection. Yeah. I think yes, how mutual information gets a good picture, but
yes, I think this will there it decreases more mutual information. After he asked that also feel that because the demonstrate of their correlation work, it's more like the correlation decreases because some of the neurons just deactivated to zero, and correlations even at zero.
Yeah, we're getting out of time, and I think Gord is seeing talk next door. Surprise! They seem to be out of speaker, and we need to prepare. See, yes, remaining next 2 minutes. Everybody. Yeah, exactly. Thank you, Yaorong. That's very interesting.
Other things we just discussed it, and there's thing they're trying to say of the background placement. Since I just read yesterday, I was thinking, does people not talking about where to put that more? So that many topics.
Yeah. It's been discussed. But there are so many. There are so many little details that people don't really think that from the start. Yes, people just say take what works without understanding how it works. So some people in my team are working to throw away, so we don't have details to think about this. Work with simple sports performance.
Yeah,
because they may not matter. Yeah, I spent last few weeks, like 3 weeks, trying to implement some fixed point iteration, and it was not working. Then I built up lots of stuff, but then it was converging, and then I threw away everything and minimized it, and it's both working and converging. But that lots of stuff that was just at home because I was using it, trying why it doesn't work, maybe this, maybe that, and then it started to work, but it wasn't stable. So then I stripped it of all of the experience. Stable. Yeah. No, not always. Sometimes. It's kind of both. They have to play hand in hand. Sometimes experience is simpler, experiment like is simpler. Sometimes theory is much faster to get an idea.
ChatGPT gets smaller. They can think.
Well, like theoretician is the joking set theoretician is like they put a plot on the board and theoretician goes and starts explaining it. They're like, whoa, wait a second, our slide is flipped. So they flip the slide. Oh, okay, I can explain that. Right? So that's a joke. Of course, theory is not quite like that. Just a little. Yeah, thank you. And see you all next week for the next